Okay, the next part, if and only if. So if you see a statement, P is true if and only if, usually written IFF, so if, P is true if and only if Q. If you see that in a theorem statement, so you're trying to prove, like, theorem P is true if and only if Q, and you then try to prove, so you're trying to prove that that's the case. You have to do two things. You have to prove, so there's two cases. So case A would be P if Q, and the other is P only if Q. Right? So the moment you see this IFF, if and only if, you're asked to give two proofs, both ways. And I'll explain in a minute what I mean by both ways. So think about it. P is true if Q. Right? For example, I live in China if I live in Xiamen. So P is true if Q. And from that you can deduce that if Q is true, then P. Right? P is true if Q. Well, if Q is true, then P. I follow that reasoning, right? So, I'll write this slightly more distinctly. So from this, you just say, if Q, then P, right? Now, what about the other case? So P only if Q. Well, there's only one way you can get P, right? And that's by having Q. So if you've got P, you must have had Q. So if P's true, then you know Q's true. Right? If you don't follow that, you play it back again. So I'll say it again. If P is true, only if Q is true. Right? So there's only one way you can have P being true, and that's when Q's true. So if you do have P, you know Q must have been true. So if P's true, then Q's true. Right? So you can rewrite P of Q as Q then P. And you can rewrite P only of Q as P then Q. Right? Now the convention is, when you have a proof that takes, when you're asked to prove P if and only if Q, you have to do two things. You have to you prove the if statement. By convention, it's pretty much a custom in pure mathematics. When giving an IFF proof, that you start with the if case first. You don't have to, it's random, but it's a convention. So most mathematicians stick to it, and they give the if case first, and then the only if case second in their proof, or two proofs. Now the if case will be if Q then P, and the only if case will be if P then Q, the other way. So in an IFF, if and only if type proof, you have to prove it both ways. You have to go this way and you have to go that way. So you start with the left-hand side and prove the right-hand side, and you start with the right-hand side and prove the left-hand side. You have to do both. In an IFF, if and only if type proof, you have to give two proofs. Okay? All right. Let's do some examples. You're asked to prove this. So two integers m and n, both even. Oh no, sorry. Two integers, their product is even. And you're asked to prove if and only if at least one of them, m or n, is even. Okay? So how to do that? Alright. Okay, so m n is even. Let's call that statement P. Right? If and only if at least one of m and n is even. And let's call that that statement, we'll call that Q, right? So this is P and that's Q. All right, let's do the if. Usually, start with the if statement first, the if case. Now, how does that work? So P if Q. Right, so P is true if Q is true. And from that you can rewrite that as if Q then P. Alright? Alright, so let's try to prove that. So the if case, if Q then P. That's the if. Well, what is Q? Well, it's here. So one of these, at least one of them, is even. So let's say it's m. So m will be of the form 2t, let's say, right? So mn then is of the form 2tn. That's even, right? That's an even number. That's even, which is p. So that's p. So we proved that, right? We started with Q and we proved that the product is P. So is even, and that's P. So we proved the if case. Now let's try the only if. The only if case. Only if. Now you can rewrite that as so P only if Q. So you can rewrite that as if P then Q. Right? So what is P? Well, Mn is even. Mn even. And what? And Q was here. So one of them, at least one of them is even. Now how do you, so we're starting with this and we have to prove that. Well, not obvious, but I'll just throw it at you. Let's use proof by contradiction. Okay. So what's the so this is your Q, right? That's your Q. So what's the opposite of Q? So what is not Q? How could you express that? Well, if it's not the case, at least one of them is even. That means none of them are even. Therefore, both of them are odd. Okay, follow the reasoning. So the opposite of this, that at least one of them is even, is that none of them are even. That means both of them are odd. Okay, so not Q implies M and N are both odd. So that means M can be written in the form 2s plus 1, and N can be written in the form of 2q plus 1, and therefore Mn is 2s plus 1 times 2q plus 1, and that's 4sq plus 2q plus 2s plus 1. And take out the 2's here, so you get 2sq plus q plus s plus 1. This here is even, right? Plus 1, so it's odd. So this number here, so Mn, this number here, that's odd. So Mn is odd. Ooh. That is not P, right? That's the opposite. P says Mn is even. We've just shown that Mn is odd. So that's not P. So we've now got a contradiction. And therefore, we can reject this. We can say, hey, that's false. So not Q is false. Therefore, not Q is true. But not Q is just Q. So we've proved that Q is true. Okay? Right. Now, if you have two statements that are like P if and only if Q, then those two statements are said to be equivalent. Right? They're effectively the same. Right? If you can prove one from the other, teething problems, right? This is my first real lecture in this series, and I'm obviously off